Students, will begin lecture number 5. So, as you know, this is a course on deep learning in material science engineering from concepts to applications. So, the last 4 lectures are the introduction. I have given you the very basic concept of artificial neural network. Basically, we have discussed quite a lot about artificial neural network. Today, we are going to talk about regularizers, the factors which will regulate the uses of neural network. But before that, let me go through some minutes about recap, whatever you have learned in the lecture number 4. So, the ANN is basically based on the concept of biological neuron, right? And biological neurons are parallel processing systems. First thing you have learned. Second, in a neuron, you have 3 important parts. First, one is the dendrite that collects the information, and then you have a cell body which processes the information. Subsequently, processed information is transmitted by axon, and through the synapse, axons then transmit the information to the next cell or dendrites of the next cell, and this goes on till it reaches the brain actually. So, we have 10,000 billion of neurons, and that is the way we can mimic such a kind of biological neuron and create structures. And I told you that how we can create such a kind of artificial structures. So, basically we can consider input or whatever the dendrites are doing as the input or the values of the x, x1, x2, x3 up to xn. Then you can multiply these individual values with corresponding weights. And I also told you the weights basically allow you to factor the effect of each of these variables. Whichever is more important, you think you can place more weights, and the variables which are not so important, you can always place less weight or lower weights. Then these multiplied factors, these are multiplied each other, added together, sum it over. We can add bias to it, and I told you bias can be because of the variation in the input values. Subsequently, this summed over thing together with variables multiplied with weights as well as bias added are fed to the activation function. Then we get an output. This output is what is transmitted by axons to the next neuron, and then again similar things done. So, this is a parallel processing system. Finally, after a certain number of layers, you can actually get an output which will be used for predictions. So, since we are going to talk about error analysis and the regularizers, output is what is important. We compare output with the actual values of the things or whatever we are going to predict, then compare and then calculate what is the error. So, idea will be here to minimize the error. That is in a nutshell true for any machine learning or deep learning algorithm. So, in order to minimize the error, we have to do certain kind of a processing. That is what I discussed in the last part of the lecture on gradient based techniques. Okay. So, gradient descent techniques. So, we will talk about more in details today, so that you understand. But you know, neurons also has a parallel things called perceptron, or basically called perceptron. This is step function, remember. It has a value between 1 and -1, 0 and -1, binary values. It can only learn examples that are linearly separable. But most of the things in material science are not so easy. They are more complex than linear things. So, we cannot use directly the perceptron, rather we can use neurons, artificial neural networks to handle that. Those ANN can handle all kinds of other things. Okay. So, let us not talk about it. So, you can build them a multi-layer network and develop things. Okay. That is what we discussed. So, activation function can be many times. The question becomes, how do you make these ANN or MLP, what is called multi-layer perceptor, learn. So, it is a supervised learning techniques. By that means, I can tell you have both the values of inputs x and the target t or y. You have both are available. That is the concept of supervised learning. Okay. So, now you can always take inputs from environment, use the neural network analysis, get an output, and you can also feed this system to the actual systems. Like in a material system, you can actually have large number of samples synthesized, properties are estimated. So, these are all actual values. Then you can compare these network predicted values with the actual values. That is why you can get the errors, right. And so, these errors are basically back propagated and calculated. So, that is why this slide become very important, that function signal moves forward directions, error signal moves backward directions. That is what is called back propagation of errors. And let us not talk about that, and back propagation we have been discussed a lot. Just to give you some perspectives, it is basically a backward pass like in football. You have World Cup football going on now in May, June, July. So, this is nothing but a back pass in football. Okay, you simply recalibrate, recalculate the weights and biases to find out the effect of these on the final output. How do you recalibrate or readjust? Basically by calculating the error and minimizing that. That is what is the back propagation is. So, it is basically nothing but a backward propagation of errors. It is the most commonly used method of training artificial neural networks in conjunction with optimization methods or regularizers like gradient descent. And what does it do actually? It basically calculates the error or loss function and take gradient of the loss function with respect to the weights of the network. So, we will soon go to the board and explain you what is that. And then this gradient what you calculate, gradient means basically slope, right, slope of a function, is calculate or used to fed to optimization method, which in turn can be used to update the weights. And this is the most important attempt or most important way to minimize the loss function, because you want to minimize the error. So, by loss, when you write loss, is nothing but a error. So, those of you who have done my course in AI/ML in material science engineering, they must have seen these terms. So, in machine learning certain kind of terms are used which may not be same as in statistics or in mathematics. So, error in mathematics statistics is what is commonly used, loss is something which is commonly used in case of machine learning or deep learning, and this is calculated simply by delta rule. Okay. So, just simply tell you what is the error. Okay. So, you can understand. Let me go to the board and tell you. So, if you have, let us say as x is your input, right, this is your input, and y is your output. That is what we have shown you in neural network also, right. So, now given a set of training samples like xi, yi, this is a set of training sample, right, x are the input variables, y the target variables or the corresponding values due to x. So, this is what is a training sample. What do you do? That means my input vectors are xi, output vectors are yi, right, that is what it is. So, now question is from the experiments or whatever actual data, you have target values ti. Target values are what? These are actual values corresponding to xi. So, every xi, let us say x1 has a target value t1, x2 has a target value t2 and goes on xn, tn. These are known to you. Okay. but this Y, they are outputs of the neural network or multilinear and perceptor network. Okay. So, this do not be confused with these two. So, now the question is, then what is the error? Error can be written as EW. Obviously, error is basically function of weights of the network, right. It will also function of biases, but for simplicity let us consider there is no bias, it is a function of only weights. So, what you can write down? So, you can write down means absolute error, which is nothing but half, then sum it over n 1 to capital N, okay, Ti, that is the target, minus Yi, and Y as a function of Xi, right, and obviously also W. You take a square of that. Absolute is because of the, that is why you have put this absolute things mod, and square is what is used. Okay, this is what is called that. So, now you know that we have to minimize this function. This is what is called a loss function. We have to minimize this function. So, to minimize this function, we calculate what is known as a gradient, right. See, it's a EW is a function of WI. So, we can always take derivatives or partial derivatives, because it's a multivariate function. So, you have to take a partial derivative. That is what I was talking about gradients. Okay. So, please keep in mind these aspects, we will get back to you more on that. So, therefore, to calculate gradients we use what is concept known as a delta rule, right. We explain you these concepts, and so I do not want to go back to delta rule again, we will simply explain you delta rule is basically when you calculate partial derivatives you have to use chain rules, that is what it is. So, now we also have a something called a learning linear boundaries. To make a nonlinear partitions on the spaces or the space, we need to define these as a nonlinear functions. So, one solution is to use a sigmoid function. Why? The important aspect of sigmoid function is that if you take a first derivative of sigmoid functions, is become like that. So, that means what? If you take a derivative of this sigmoid one minus, that is what it becomes, right. That is why you use this. So, it basically becomes clear that we can use nonlinear partitions in space to learn nonlinearities. Okay. So, how this works? Just to tell you again, see, it works like if there is a 3 phases. First phase is propagation, forward propagation of these training patterns input through this neural network, to generate the propagations output activations, right. That means, first you have to take the variables, multiply with weights, add the biases, sum it over, put an activation function, get an output. Then backward propagation of this propagations output activations through this neural network using a training pattern in order to generate the deltas. Deltas mean difference between the input outputs with all the hidden as well as non-hidden layers. In the once you get that, you can calculate gradients of these, but the deltas with respect to the difference of values between the actual output and the predicted values, and then get the gradients, multiply its output data delta and input activation to get this gradient of the weights, subtract a ratio of the gradient from the weights. Okay. That is what it is done. So, this is simply done in this case. I will not discuss much about that since we have discussed about it. So, let me just go back to the optimizers. So, what do you think our optimizers or regulations are? So, optimizers is we have already talked about a little bit. What are these? So, these are used in deep learning to prevent overfitting or to get a better estimation of the errors or Rather I could say to get quickly the weights to be balanced out. These are the aspects, that is why they are used. Okay. So, by adding the constants to these functions, we can actually control or regulate that. So, let me just tell you a little bit about that, then we will get back into your actual aspects. DL, it requires us to optimize the error functions, and let us take f as error function. We have used E there, we can use f as error functions. It is a single variable function x, right, and it is a scalar valued function as is shown in this case. So, what do you do? This is like this, let us say. Am I clear? If this is like that, so as you know that it has many optimum things. So, first of all, you see there are local minima, one is here, sorry, lower maxima, and there is a global maxima here, clear, you can see that. Then you have a local minima, this is the another one, and then you have another one local minima, and finally you have a global minima. So, this is global minima, this is global maxima. Am I clear? So, you can also have saddle points, we will talk about it. So, since DL requires very complex set of data, deep learning, you can have all kinds of situations. Now, our aim is to minimize the error. That means, we should, by analyzing of this function, we should hit the global minima. But there will be always a possibility that instead of reaching the global minima, we may reach this local minima. Then the error will not be minimized, all your weights will not be properly optimized. That is the problem. So, finding this optima of saddle points requires you to calculate what? Derivatives or gradients that you have learned from mathematics. If you have function f(x), okay, f(x), so first thing you take as a first derivative, put it into 0, find the values of x for which this value is 0, then take in the second derivative, and if you find second derivative is negative less than 0 for some certain values of x, then that corresponds to the maximum, right, and if it is f double prime x double derivative is more than 0 for certain value of x, then it is called a minimum. By doing that, you can find out all these points. This is what you have learned in mathematics, right. That is why you calculate gradient or slopes, okay. But magnitude of derivatives at a point, what we can talk is basically can change depends on the values of the x. Secondly, it is also rate of change of the function at the point. So, derivatives become 0 at these stationary points, we call them optimum points or optima points or saddle points. So, if functions become flat or if the derivative goes to 0 if you change the x by a little in such points, right, that is the idea. So, these are the points of fluctuations, functions as maximum minimum points, all this we know, right, this is what is we have learned from your literature, okay. So, now what is the derivative, how do you define derivative, you know that dfx by dx is nothing but a limit delta x goes to 0 del fx by x del x, right, that is what it is. You should have learned from your calculus. Am I clear? So, you can show on a very nicely on a chart on a plot like this. This is let us say fx, this is your x. So, you have seen the function. Okay. So, as you know, if I take a let us say delta x, correct, that is what I am talking about it, okay. Similarly, you can do other places also. This is what it is. So, derivatives are actually important in the sense of calculating the rate of change of functions at a particular point on the functions. And your derivatives also have certain rules, right? You know this, that sum rule, scaling rule, product rule, quotient rule is very important. You can see that this is what is the quotient rule. You have to take a square of the denominator and then take this numerator as like this, one function derivative, second function not, third then minus second function derivative multiplied by the first function. Okay. And you have a chain rule also. Chain rule you should know, very simple chain rule. So, now coming back to the saddle point. What are saddle points? Okay. So, let us first discuss about the saddle points. Okay. Let us first do that, then we will come back to the aspects, to the derivatives. Points where derivative goes to 0, but they are neither minima nor maxima. Very difficult to understand, right. So, let me just take these pictures through you. This is taken from of convex.org. So, you see this curve has a local minima here, right. This curve has a local maxima here. Can you see that? So, these are not saddle points. Saddle point is like this. When you do a horse riding, you can see, you can feel the saddle point there, saddle actually. So, you can see that this is not a minima or this is not a maxima, but this is a part of the function where derivative is 0. Okay. So, now here this is a function, let us say f x versus x, right. So, you can clearly see here this is a local minima, this is a global minima, this is a local, sorry, this is a local maxima, this is also global maxima, this is a local minima, this is also local minima, right. So, this is also local minima. Okay, that it looks like this is looks like a global minima, right. So, what is the saddle point? Saddle point is here. You can see that it is exactly like the same thing here in 2 dimension. So, at the saddle point also the derivative is 0, but this is not a minima or not a maxima function. So, you can have situations in a deep learning complex function situation like that. You can have all these kinds of situations possible, that is what we are discussing. So, saddle points are very common for loss functions of deep learning, and we have to handle them very carefully during optimization. So, second or high derivatives can help actually. Second derivative means double derivative or triple derivative, second order, third order derivatives which we call, can help to identify if a stationary point is a saddle point or so on. But you know, majority of these functions in case of deep learning or machine learning, they are not single variable functions. Like f is not a function of x, but f may be a function of x, y, z or many other variables. So, that means majority of the functions we see in machine learning or deep learning are multivariate functions. Okay, this is taken from benchmarks fcns.xyz. Okay. So, you see here there is, this is the function is basically the fx is a function of x1 and x2, you can see that. So, this is a multivariate functions. So, if you take from the top view of the functions, you see these are your these aspects, this minima and maxima, maximas are here, minimas are here. So, you can see all of this, you can clearly see that. So, how to find out then this kind of minima and maxima in a multivariate functions, and to be specific you should be expert on doing that in such a kind of situations. That is what is important, right. So, we discuss about multivariate functions, let us see how we can do that. So, therefore, for a multivariate functions what you do? So, gradient of the functions is basically defined by that. You can clearly see that gradient of, that is a grad operator, fx is basically, this I call partial derivatives, del f del x1, del f del x2, del f del x n or d or whatever. So, that means fx can be written as dimension d is R is a space. That means what? R is d cross 1 vector of partial derivatives. That is what it is. If you put it together, we will see that in a quickly time. Optima and saddle points can be defined similar to one dimensional case, right. That means we need to require the properties that we have seen in case of one dimensional case. What are the properties we saw? Very simple. First derivative going to 0, here it will be partial derivatives will go to 0, and second derivatives in this case is known as a Hessian, remember this, okay, Hessian second derivatives. So, what is that? Let us talk about a little bit of Hessian. So, we understood, right. So, optima and saddle points can be defined similar to the one dimensional case. I can go back and tell you that, discuss. In one dimensional case, what we are doing? We are taking derivatives, right. This is the one dimensional case, right. So, you can clearly find out that. For the saddle points, you have to take the second derivative also, because saddle points you have a curvature change. You can see that curvature is changing. This is one curvature, this is one curvature. So, there the second derivative will not become, it is also 0 second derivatives, because that is what the inflection point is. Okay. So, this is what it is. So, okay, let us talk more about Hessian, and I told you Hessian is nothing but a what? Second derivatives for the multivariate functions. So, what is that? Hessian is defined like this, okay, am I clear? It is basically a matrix form in terms of second order derivatives of each of these functions. Okay. So, when you write del 2f del x1 x2, we mean to say it like this, okay, that is what it is. So, that means here this Hessian is a D cross D matrix, okay, that is your Hessian. So, now how Hessian can be used? Hessian can be used to access the optimum values of saddle points. So, first if you take first derivative to be 0 and second derivative positive, then we can call x as a minima. Similarly, if the first derivative is 0, second total derivative is negative, we can call x as a maxima, same as like in case of single variables functions. Okay. So, that is how it is, but you have to calculate the Hessian and then find out first derivative, second derivative. First derivative is again simple, okay, you can use chain rule to do that. Second derivative what is called as a Hessian. So, let me stop here, I will come back to the second part of the lecture where I will discuss more about this, how this can be used as a regularizer.